Hi 111, in this last video for section 2.1 we're going to finish our work talking about functions, and we're going to begin our discussion today with talking about how we can find the domain of a function. In some instances, it may be just that we have the equation of a function, for example, and we don't have its domain explicitly given to us. So we have to figure out exactly what the domain is. What are we allowed to plug into the function? What are the inputs allowed to be so that we get an output which is a real number? Right? And so if, for example, over here in our notes, we see that if the domain isn't specified, if we're not explicitly told what it is, right, then we say that the domain of the function f is the largest set of real numbers for which the value of the function, right, the output of the function, is a real number. Okay, so we want to include as many values for the input as possible, right? We want this club to be as open and welcoming as possible, right? But we want to make sure that anything we plug in has a corresponding output. Okay. So let's see exactly how this would work, right? So let's try an example, right? So let's consider a function. So let's try an example. Oops, I'm still working with red. Let's switch that to black, a little friendlier of a color. Okay, so let me give you a function maybe that looks something like this. How about 3x squared plus 2x plus 1. Okay. Now remember, this is function notation, right? This is an equation that's written explicitly, right? This is y equals f of x equals 3x squared plus 2x plus 1, right? The output would be y in this case, right? Okay. I didn't write the y equals because usually we don't if we use the f of x notation here, but it's sort of implied, right? It's implied that the output is the y variable here. Okay, so this is a function. It's using function notation, so we know it's a function, right? But notice I haven't written anything about the domain, right? There's no circle of mappings to say what the inputs are allowed to be. There's no table, right? There's no list of ordered pairs. There's nothing, right? We don't have any idea here. So what we have to do is follow a process to figure out what the domain of this function actually is. Okay, and over here notice I've outlined a process for you. Okay, so it says to find the domain of a function defined by an equation, and that's exactly what we have here. First, we start with the domain as the set of real numbers. We start with as much as we possibly can. Okay, we start with as many numbers as we can, meaning everything. We start with a set of real numbers. That's everything for us. Okay, we don't want to include complex or imaginary numbers, right? The I stuff, nobody wants to do that, so let's not include those in our possibilities. So include all real numbers here. Start with everything. Then what we do is we start tossing out numbers. Okay, we exclude from this set of numbers anything that makes any denominators equal to 0, or we exclude any numbers that make there be a negative number inside an even root, like a negative inside a square root, because we all know that bad things happen when that happens. So what we have to do here is look to see, do I have any denominators? Nope. There's just 3x squared plus 2x plus 1, so there's no denominators. There's no value of x that when I plug it in, or when I use it as an input, is going to make like a 0 in a denominator, right? Like no division by 0 or anything's going to happen. And there's no radicals either. There's no square roots, no cubes, fourth roots, nothing like that. So what we can say here is that there's not going to be any special values of x or inputs here that we need to be aware of, right? And if we think about this carefully, if we plug in any value of x, right, we're going to get an output, right? Because remember that we take an input here, we square it, multiply it by 3, add 2 times that input, and then add 1 more, right? We can do that with any real number we like. Okay, so what that means is that we don't have to toss out any values of the input, right? Anything we like can be plugged in. So what we say here is that the domain is just all real numbers. I don't know why my pen is being so messed up. This looks awful. Let me get rid of this. This is terrible. So bad. Okay, there we go. All real numbers. Okay, so we can say the domain is all real numbers here. There's actually a really fancy way to write all real numbers, and you can impress your friends at parties and stuff if you want to know how to write this. So to denote the set of all real numbers, the collection of all real numbers, right, as a set, you can just write this fancy R for the word real, right? It's an R with two vertical back lines, right? So that right there, that double backed R right there, that means all real numbers. So if your domain is ever all real numbers, you can just write that double backed R and I will know what you mean, and all sophisticated mathematical people will know what you mean. Okay? So let's consider another example here. Maybe something like, how about this? 2x over x minus 4. Okay, so that's our function here. Okay, this one looks a little different, right? Yeah, so it says take your input, which is x, whatever it is, so do 2 times that number and then divide by that number minus 4. Okay, so for example, if you were to plug in 1 here, right, you would do 2 times 1 divided by 1 minus 4, and you'd get a number. Okay, but I'm not worried about trying to find values of the function here. I'm actually wanting to find the domain of this function, right? So let's see, we go through our process here. We start with the domain as the set of real numbers, so start with everything, right? So include everything, all real numbers. Now what we have to do is toss out any values of the input here that would make a 0 in a denominator. Well, notice that there is a denominator right here, right? This x minus 4 here. And is there a value for x? Is there a certain input that we would not want to see plugged into this function? Well, notice that if we ever tried to plug in a 4 into this function here, what would happen? We would do 2 times 4 divided by 4 minus 4, right? So let's see what would happen. Let me just write what that would look like for you. So if I tried doing this, f of 4, right? This would be 2 times 4 divided by 4 minus 4. Okay? And that's bad, right? Right there, see that denominator? Bad. Sad face, right? That's bad. The reason that's bad is because that's a 0 in the denominator, right? We cannot do that. Division by 0 is not allowed, okay? Which means that we've just found an input that doesn't produce an output number for us, right? This is 8 divided by 0. That's not a real number, right? Okay, so what that means is that we're not allowed to plug in 4. 4 cannot be in the domain of the function, right? We can't include that in the set of numbers that are allowed to be used as inputs, right? We can't use that number. Okay, so we've got to throw that out, okay? So how would we write the domain then for this thing? So we got to write domain. Well, let's see. There's a couple ways you could write this. A lot of people like to just write something like this. They like to write x can't be 4. Okay, and they just leave it like that, right? Another way to write this is making use of interval notation. So let me get a fresh piece of paper here. Okay, so we want to say that we want to say that the domain is going to be what? All values of x except for 4, right? So remember that one way we can do that is to use interval notation. I want to just exclude the number 4 from my number line, right? I want to say do everything but 4. Okay, so another way to do that would be to use this interval notation and say I want everything from negative infinity up to 4, but not including 4. But I also want everything on the other side of 4 as well. So I union that with starting at 4 but not including it, and everything positively, right, in that direction. So remember, in terms of a number line, right, if you were thinking about number lines here, that really means that you want everything from this to here, and if this is 4, oops, if this is 4 right here, you don't want to include that stuff, right? So you want everything this way, and you want everything this way, but not actually 4 itself, right? Open circle right there. And you could even make it more obviously an open circle by maybe erasing that right there, okay? And making that a big open circle. Okay, good. So that's one way you can write it, the interval notation or the x not equal to 4. There's also a fancy set builder notation that your book talks about, and it makes use of those curly brackets to denote a set, right? And so there's a certain way to format this, right? So it says the set of all x's, right, such that, and that's what that vertical bar means, right? So that means such that. Okay, such that, and you want to say the set of all x's so that the following thing is satisfied. So you can say x not equal to 4. Okay, So you read this as the set of all x's such that x is not equal to 4. Okay, and again, that's equivalent to saying all real numbers except 4. And if you want to just write that, that's totally fine too. Okay, so that's one way we can find the domain of a function. Let's maybe do one more example, and then we'll move on to some properties. Okay, so let's maybe think about something like this. What if I define a function by this thing? Okay, so this function says you take an input, you do 1 minus that input, and you square root that result. Okay, so let's think about finding the domain of this thing, right? So remember, we start in terms of our process, we start out by saying start with everything, right? Start with all real numbers, and let's throw out anything that is bad, right? So in number 2 it says throw out any numbers that make 0 in a denominator. Are there any denominators? No, so I don't have to worry about that one. But the next one says throw out any numbers that make a negative inside an even root, like a square root. We have a square root, right? So what we want to do is make sure that the stuff inside the radical, this 1 minus x stuff, we want to make sure that that always gives us a positive number, meaning we want to make sure that this is always true. We want this 1 minus x, the inside stuff, to always be positive, right? Okay, because if that stuff's always positive right here, if that expression 1 minus x is always positive, then you're always taking the square root of a positive number, right? This is what we want to ensure, right? That the stuff inside of the radical is always positive here, okay? And I'm being very bad with notation, right? But I just want to make sure the stuff inside the radical is positive. It's also okay if the stuff inside the radical equals 0, because remember the square root of 0 is 0, right? And that's totally fine. Okay, so just don't be scared about that part, right? So that's allowable here. It's okay for the inside stuff to be equal to 0 and or positive. Okay, so what does this mean? Well, if this right here is our restriction about the inside being positive, well, notice, doesn't that mean then if I add x to both sides here, okay, that means that I get 1 has to be greater than or equal to x. Okay, and if you don't like seeing your inequality like that, the equivalent way to write this is that x has to be less than or equal to 1. Right? And so what does that mean? That means that these are the okay inputs, right? These are the values of x that are okay, right? The ones that are less than or equal to 1, those inputs will be okay to plug in, right? So, I mean, just to check this, think of a number that's less than or equal to 1. How about -2? Is it okay to plug in -2 into this function, right? Is -2 an okay input? Well, 1 minus a -2 is 1 plus 2, which is 3. And the square root of 3 is a real number, right? So we get out an input when we plug in any number less than or equal to 1, right? And that's what we're looking for here. Okay, so to actually state our domain here, it would be okay to say, you know, you could just write x is less than or equal to 1, right? You could write x less than or equal to 1. That's totally fine. You could also use interval notation, right? So how would we write this as an interval? We want all values of x less than and or equal to 1, right? So let's see, I want all negative stuff and then up to 1 and including 1. Again, if you need a review of interval notation, remember to do the Appendix 9 problems that I posted to Moodle. Okay, so that's another way to write this. You could also do the set builder notation, which would be to say the set of all x's such that x is less than or equal to 1. Okay, and we can't really use that double R notation here because we're not saying that the domain is all real numbers, right? So we shouldn't use that here. There's maybe a fancy way to do it, but for right now, we're not going to do that. Okay, so that's how we can calculate the domain of a function. The last thing for this video, we'll go a little over on time in terms of the 15 minutes here. I upgraded to Pro, so we were able to go a little longer than 15 minutes now. But the last thing I wanted to do for section 2.1 to finish off this section is to talk about properties of functions. So what's cool about functions is that they're able to be used to do algebra, right? You can add them, you can subtract them, you can multiply them, you can divide them. You just have to think about doing that just like you would any other algebraic expressions, right? You can add two expressions of x together, right? You just do what? Combine like terms, okay? And so you can do the same exact thing with functions, okay? And so if you'd like to know in your textbook, this is on page 65, right? The properties are on 65, and there's an example on the next page here. But what's really important is just to think about these properties in terms of them being operations on functions, right? If you want to add two functions, well, this is all just special notation here, right? All this says is that if you wanted to add two functions here and then give it an input, it's the same as giving that input to each of the two functions independently and adding the result, right? So it's thinking about the order in which things are happening here, right? You add the two algebraic expressions here, and then you plug in an input and get an output. That's the same as if you plug an input into each one, get out an output, and add the outputs, right? Okay, so this is going to help us really more algebraically than anything, but it allows us to operate on functions. You'll see what I mean in a second when we do an example. Okay, but the difference here, same thing. If you want to subtract two functions, just subtract their algebraic rules here. Okay, multiply them, same thing. Divide them, same thing. Just make sure that that denominator function is never 0, right? Because we don't want to divide by 0. So let's get through this theory part of this, right, this abstractness over here, and let's actually consider an example. Okay, so let's maybe take two functions. So let's say f of x is 3x squared plus 1, and we'll say g of x, and this, okay, so this might make you nervous, right? So more than anything, maybe the notation might make you nervous here, because you're probably saying, wait, a function is f of x, right? Well, the only reason we use the letter f is because the word function starts with f. Okay, we didn't have to use an f. We could have used any letter we like, right? So let's say, I mean, if you have two different functions, right, it's okay for there to be two different functions. I can't both use the letter f, right? Because f is the name of the relation, which is a function, right? Remember the little mapping circles? I drew a little f with the arrow on top, right? That's the name of the relation, which is that function. Okay, you don't want to use the same name twice, right? That might get confusing. So what we do is we call them two different things. We can call this one f, and we can call this one g, right? It's still a function, it's just called a different letter. Okay, so this is g of x, right? And so let's maybe call it, how about x minus 4? Okay, so again, I've got two functions, right? They're functions because we're using function notation, right? Okay, and if you think about the domain of each of these functions, notice that there's no fractions, there's no radicals, there's nothing crazy going on, right? There's no denominators, okay? So the domain for each of these is just all real numbers, because you can plug in any input you want, and the operations here are just plug and chug, right? You multiply, add, or subtract, or whatever. You can do that with any real number you like. So the domain for each is all real numbers. Let's try adding these two functions together. So how would I do f plus g of x? Well, by definition, f plus g of x is f of x plus g of x. Okay, so what do? Well, I take the rule for f and I plug it right there, and then I add the rule for g, and I just work with them in terms of algebraic expressions, right? So this means I do 3x squared plus 1, excuse me, plus x minus 4. Okay? And if you like, you can use some little parentheses here to emphasize that it's f plus g, right, those two functions. But really what we're going to do is just add them together, combine like terms. So 3x squared plus x, and 1 and negative 4 is minus 3. Okay? And that's a new function, right? Notice that that's the function f plus g of x, right? So this is a new function, okay? So adding two functions results in another function, okay? And that's the whole point of this, is that we can do operations on functions, add, subtract, multiply, and divide them, and we get a new function. So let's try subtracting them. F minus g of x, okay? By our definition, f minus g is, I just do f of x minus g of x, right? So I do f of x minus g of x. Okay, so let's do the same exact thing we did before. I need to do f of x minus g of x. Okay, so 3x squared plus 1 minus x minus 4. Okay, now let me ask you this. It says all of f minus all of g, right? If I look at what I've written so far, it says all of f minus, does this say subtract everything that is g, or does it say just subtract the first term, right? I need to be very careful here and say I want to subtract everything that defines g of x, right? Everything that is g of x. So what that means is that I need to be really careful and make sure I use parentheses here on that second function. We could put them here in the first one too, just for emphasis. Just like up here in this previous one, we could have put parentheses like this to emphasize that it's the sum of those two expressions like that. But here, it's actually crucial that you do so, right? Because now it says everything that is f of x minus everything that is g of x, okay? Those second parentheses are crucial. You gotta have those, right? Okay? Because now it says what? When I combine like terms here, it's 3x squared, and then what do I have for x? Minus x, and this is 1 minus a minus 4, which is 1 plus 4, which is 5. Okay, if you hadn't used those second parentheses there, you would have gotten 1, what, minus 4. So you would have gotten a minus 3 here, which is not correct, okay? So we gotta have those parentheses for that second part. Okay, let's just do the multiplication and the division here just to finish out this example. So let's do f times g of x. And I know this video is a little bit longer, sorry, but 2.1 is a long section, right? So to multiply these two functions here, notice that I do f of x times g of x. Okay, so f of x times g of x. Okay, and so what this means is I need to do what? Everything that was f of x, so that was 3x squared plus 1, all of that times everything which was g of x. So let's go back a second. I think I made it x minus 4. Yep, x minus 4. 3x squared plus 1 times x minus 4. Okay, and how do I multiply these two things? Well, they each have two terms, right? 3x squared plus 1, right? So that's two terms. This one has two terms. I'm going to have to FOIL this thing out, right? So the first part is 3x squared times x, which is 3x cubed. The outside part is 3x squared times minus 4, which is minus 12x squared. The inside part is 1 times x, which is x. And the last part is 1 times negative 4, which is negative 4. And notice this one is already done. There's no like terms to combine, right? All the powers of x are different, so that one's finished. And last, let's do f divided by g of x. And I do that by doing f of x divided by g of x. Okay? Alright, so, and remember the caveat for this to do f of x divided by g of x is that g of x can't be 0. Well, our g of x is x minus 4, so it's not 0, right? We're not plugging in the 0 function here, the thing that's always 0. We're not plugging that in down there, so we're okay. Okay, so let's go ahead and do this. So this is 3x squared, oops, plus 1 in the top, divided by x minus 4 in the bottom. Okay, great. And so that's it, right? There, we can't do anything more with that. You can't cancel the x's because things are joined with addition and subtraction, so that's just finished, right? Okay, so what I'd like you to do is to look at the example number 11 in your textbook, because that one talks about how to find the domain of functions when you do operations on them. The whole point of it is that you just want to make sure that the two functions that you're working with here, working with operations, you just have to make their domains agree. You take the stuff that they have in common, right? But we're not going to emphasize it very much for now, but just look at example number 11 in your textbook, and that's on page 66. Okay, so check out that example, and that finishes section 2.1 for us. Our next video is going to be on section 2.2, which talks about graphs of functions.